Have you ever wondered how your digital kitchen scale gets the weight of that flour just right, down to the gram? Or how engineers can spot these tiny, invisible stresses in a massive steel bridge? Well, the secret, a lot of the time, is this really clever and surprisingly simple circuit that was designed over 150 years ago. Today, we're going to break down the Wheatstone Bridge. So here's our game plan. We'll start with the basics, what this thing even is. Then we'll get into the core principle that makes it so cool, this idea of balance. We'll even jump into the math to see where its famous formula comes from. After that, we'll tackle a real example of an unbalanced bridge, and then we'll wrap it all up with the key takeaways.
All right, let's dive right in. First question, what in the world are we looking at when we talk about a Wheatstone bridge?
Okay, here it is, in all its glory. A Wheatstone bridge is basically an electrical circuit that's built to measure an unknown resistance with some serious precision. And the way it works is by balancing two different legs of the circuit against each other. As we're about to see, it is a fantastic, real-world application of Kirchhoff's rules, which, if you remember, are like the fundamental laws for how current and voltage work in any circuit. Let's break down the parts here. It's actually pretty simple. You've got 4 resistors, kind of set up in a diamond shape. Then you have a power source, like a battery, connected across 2 opposite corners. We call that the battery arm. And then, and this is the important part, across the other 2 corners, you connect what's called a galvanometer. That's just a super sensitive meter that can detect even the tiniest little trickle of electric current. This whole middle section is called the galvanometer arm, and it is the key to everything. So how does this whole setup actually help us measure something? Well, it all comes down to a concept called the principle of balance. This is the real magic trick that makes this bridge so incredibly useful. Okay, here's the core idea. We say the bridge is balanced at the exact moment we adjust the resistors just right, so that zero, and I mean absolutely zero current flows through that galvanometer in the middle. The current in that middle path, which we'll call I sub G, has to be nil. So when that little needle on the galvanometer doesn't even twitch, when it shows a null deflection, we know the bridge is balanced. But why? Why does the current stop flowing? It's because points B and D in the circuit are at the exact same electrical potential. Think of it like this. If you have 2 pools of water that are at the exact same height, water isn't going to flow between them, right? Same thing with electricity. No potential difference, no current. Simple as that. So we know what happens, but now let's get into the why. How do we actually prove this relationship with math? It's time to do a little derivation, and you'll see how this whole thing is built right on top of Kirchhoff's fundamental laws. Okay, let's build this formula. We're going to start with our most important condition. The galvanometer current Ig is 0. That makes our life so much easier. Now, we apply Kirchhoff's loop rule, which just says that if you go in a full circle in a circuit, all the voltage changes have to add up to 0. So let's look at the top loop, ADBA. Applying the rule there gives us our first equation, minus I watt R1 plus I2 R2 equals 0. Got it? Now for the bottom loop, CBDC. Same rule, different loop. That gives us our second equation, I1 R3 minus I2 R4 equals 0. Now that we've got these 2 equations, believe it or not, the hard part is over. From that first equation, we can just rearrange it to say I1 R1 equals I2 R2. And from the second one, we get I1 R3 equals I2 R4. All we have to do now is put them together. And here is where it all comes together. If we just divide that first rearranged equation by the second one, the currents, the I1 and I2 terms, they just cancel each other out. And we're left with this beautifully simple, elegant, and super powerful formula. R1 over R2 equals R3 over R4. That's it. The ratio of resistances on one side of the bridge has to equal the ratio on the other. This is the balance condition. And what it means is, if you know 3 of those resistances, finding the 4th is a piece of cake. Okay, so that's the perfect balanced world. But what happens when those ratios aren't equal? Well, in that case, current is going to flow through that galvanometer. So let's walk through a real-world example and see exactly how to figure that out. So here's our problem. We've got a circuit with all the resistance values laid out, and it's powered by a 10-volt source. Now, you can see right away that the ratio of 100 to 60 is definitely not the same as 10 to 5. So we know for a fact this bridge is unbalanced. Our job is to find the exact current that's flowing through that galvanometer in the middle. And here are all our numbers laid out nice and neat. We've got our 4 main resistors. And notice this, the galvanometer itself has some internal resistance, 15 ohms in this case. Plus, we've got our 10-volt source. With all this info, we have everything we need to use Kirchhoff's rules one more time. Okay, let's do this. But remember, this time IG is not 0, so things are going to be a little more involved. Let's start with that top loop, B, A, D, B. We apply the loop rule, and we get our first equation. 100 times I1 plus 15 times IG minus 60 times I2 all equals 0. One down. Now for the bottom loop, B, C, D, B. And here, we got to be really careful about how the current is splitting. The current going through that 10-ohm resistor is what's left over from I1, so it's I1 minus IG. And the current in the 5-ohm resistor is I2 and IG coming together, so it's I2 plus IG. You put all that into the loop rule, and you get this slightly more complicated second equation right here. So at this point, we can take off our physics hat and put on our math hat. This isn't really a circuit problem anymore. It's just a system of simultaneous equations. Our whole goal now is just to do the algebra, substitute and simplify things, until we can get IG, the galvanometer current, all by itself. And after you run through all that algebra, crunch the numbers, here's our answer. The current flowing through that galvanometer in this unbalanced bridge is 4.87 milliamps. It's a small current, for sure, but it's definitely not 0, just like we predicted. All right, let's take a quick moment to summarize the most important ideas from all this, just to make sure they really stick with you. So, to recap, the absolute heart of the Wheatstone bridge is that balance condition R1 over R2 equals R3 over R4. Its main job, its whole reason for existing, is to use that simple ratio to measure an unknown resistance with incredible accuracy. And if you ever run into a bridge that's unbalanced, you know what to do. You break out Kirchhoff's rules and you can solve it. So I'll leave you with this final thought. This principle is old, like 19th century old, but its elegance and its precision are absolutely timeless. So where do you think this basic idea of a balanced bridge is still being used today? Think about anything that needs to measure a tiny change in resistance. I'm talking about digital scales, strain gauges on bridges and airplanes. How does this simple, brilliant circuit still form the foundation for so much of our modern technology?